Welcome to Episode 4 of the 5 Domains series. Domain 4, Manage AI Model Development and Evaluation, 16% of the exam. This is the technical heart of the AI project. Domain 4 is where models are built, trained, and evaluated. But this is not a pure data science activity. The PM owns the experimental process, compute resources, team coordination, and the quality gates that determine whether a model is ready for formal evaluation. Two things only the PM can guarantee: a baseline before any complex work begins, and experiment tracking before any experiment is forgotten. Let us begin.
Domain 4 covers 9 sequential steps in Phase 4, plus evaluation activities in Phase 5, and model update responsibilities in Phase 6. Step 1. Algorithm selection. Based on problem type, data characteristics, and non-technical constraints from Phase 1, latency, explainability, resource limits, the team selects candidate algorithms. For tabular data, gradient boosting methods like XGBoost and LightGBM are typically the starting point. For images, convolutional neural network architectures. For text generation and conversational AI, large language models with retrieval-augmented generation. The algorithm choice is not purely performance-driven, it must also satisfy the deployment constraints. Step 2. Baseline model. A simple reference model, logistic regression, shallow decision tree, must exist before any complexity. It answers, does the complex model actually improve on the simplest approach? Step 3. Model training on the training set. The model learns from labeled examples. Training set only, never the validation or test set. Step 4. Hyperparameter tuning. Grid search, random search, or Bayesian optimization with Optuna. Budget compute explicitly, before this step begins. Step 5. Experiment tracking with MLflow, or weights and biases. Every experiment recorded algorithm, hyperparameters, data version, code commit, validation results. Non-negotiable. Step 6. Validation set evaluation. Compare candidate models on the validation set, using the metrics selected in Phase 1. Not the test set. The test set is sealed. Step 7. Fairness testing. Disaggregate validation performance by sensitive group. Domain 1 requires this in the development loop, not only at Phase 5. Step 8. Explainability check with SHAP or LIME. Are the features driving the model consistent with business understanding? Is the model relying on a proxy feature for a protected characteristic? Step 9. Model versioning. Save best candidate models with full metadata. Enables reproducibility, recovery, and Phase 5 evaluation. In Phase 5, Domain 4 supports formal evaluation on the sealed test set and error analysis. In Phase 6, Domain 4 retrains when drift is detected. Domain 4's contribution evolves across the lifecycle. In Phase 1, Domain 4 defines the technical problem type, classification, regression, clustering, anomaly detection, reinforcement learning, and identifies the non-technical requirements that will constrain algorithm selection. Can the model take more than 100 milliseconds to respond? Does the regulatory environment require an explainable model? Can the model consume more than 4 GB of memory in production? These constraints must be recorded in Phase 1, because they directly affect which algorithms are even viable in Phase 4. In Phase 2, Domain 4 participates in EDA to assess problem complexity. Are the relationships in the data likely linear or nonlinear? What features look most promising? These early signals help Domain 4 form a preliminary algorithm hypothesis, which it will test systematically in Phase 4. In Phase 3, Domain 4 collaborates with Domain 3 on feature engineering. Domain 4 proposes which features to engineer, based on algorithm requirements and problem understanding. Domain 3 executes the transformations. In Phase 4, Domain 4 leads entirely. All 9 development steps belong here. The PM's role is to ensure the process is scientific. Baseline first, experiments recorded, fairness checked, weekly review meetings held. In Phase 5, Domain 4 supports evaluation by selecting appropriate metrics for the problem type, running the final evaluation on the sealed test set exactly once, conducting error analysis to explain where and why the model fails, and assessing explainability outputs. In Phase 6, when data drift or concept drift is detected, Domain 4 analyzes root cause and builds the updated model. The PM must plan Phase 4 reactivation as a recurring operational event, not a one-time project deliverable. Now let us look at the PM's 4 specific responsibilities in Domain 4. 4 roles define what a project manager must actively do in Domain 4. The first role is Compute Resource Manager. Training, especially deep learning, consumes significant GPU compute. Unmanaged. Resource conflicts and cost overruns. Responsibilities. Estimate compute needs before Phase 4. Allocate for parallel experiments. Monitor GPU utilization. Set budget alerts. Use spot instances for tuning experiments to reduce cost by 60 to 80%. The second role is Experiment Process Enforcer. Data scientists run dozens of experiments and keep results in notebooks or memory. 3 months later, the best model cannot be reproduced. Responsibility. non-negotiable tracking from day one. One shared tool, MLflow or W, and B. Every experiment records, objective, algorithm, hyperparameters, data version, commit hash, validation metrics. Check the dashboard yourself weekly. The third role is data scientist and engineer coordinator. Conflicts, model too large, inference too slow, surface at phase 6 deployment, if not managed earlier. Responsibility, establish the handover format before phase 4 begins. Joint sessions, engineers present operational constraints, data scientists present model choices. Resolve conflicts against phase 1 non-technical requirements. The fourth role is weekly experiment review organizer. Without checkpoints, phase 4 drifts for weeks. Agenda, review tracking dashboard, identify best and failed experiments, agree next week's plan, flag resource or timeline issues. 45 minutes, non-optional. 4 risks define the Domain 4 failure landscape. Risk 1, overfitting and underfitting undetected. Overfitting, high training accuracy, poor validation. Underfitting, poor accuracy on both. Both produce models that fail in production. Defense, require learning curves. Plot training versus validation performance per epoch. Growing gap equals overfitting. Both plateauing low equals underfitting. Require this at every review meeting. Enforce regularization, dropout, depth limits, and cross-validation for small datasets. Risk 2, wrong algorithm selected. 2 forms, defaulting to deep learning for every problem, or optimizing for accuracy while ignoring phase 1 operational constraints. Model too slow, too large. Defense, formal algorithm selection rationale referencing problem type, data characteristics, and phase 1 constraints. Baseline comparison for every candidate. Complex model that barely beats baseline is not worth the investment. Risk 3, no experiment tracking. Team cannot reproduce its best model. Reruns already completed experiments. Cannot demonstrate development process to regulators. Defense, non-negotiable tracking policy from day one. One shared tool, standard fields, enforced by PM. Risk 4, data leakage in phase 4. 3 forms. Temporal leakage and time series lag features. Feature leakage from future-informed fields, and using test set statistics for hyperparameter decisions. Defense, every feature justified with, is it available at prediction time? Time-based splits for time series. Test set never touched in phase 4. A furniture manufacturer needs to forecast raw material demand for the next 3 months to optimize inventory. 3 years of sales data prepared. Holiday calendars and promotion schedules included as features. KPI-MAI below 15% for the 1-month forecast horizon. Algorithm selection rationale. Tabular time series data. 36 months of observations. Interpretability valued by the operations team, and latency is not a constraint. XGBoost is selected as the primary candidate, with linear regression and ARIMA as baseline comparators. Critical data split decision. Time-based split, not random. Training data covers months 1 through 30. Validation data covers months 31 through 33. Test data covers months 34 through 36. This split structure must be enforced before any experiments begin. Random splitting would produce temporal leakage and artificially inflated performance estimates. Baseline results. ARIMA, MAI 24.1%. Linear regression, MAI 21.8%. XGBoost Experiment 1. Default parameters, MAI 19.2%. Better than baseline but not at target. Overfitting detected. Training MAI 12.1% versus validation MAI 19.2%. XGBoost Experiment 2. With regularization, max depth reduced, learning rate reduced, MAI 16.8%. Overfitting reduced. Learning curves now converge. XGBoost Experiment 3. After feature engineering, adding week of year and holiday proximity features, MAI 14.3%. Target achieved. All 3 experiments recorded in MLflow, with algorithm, hyperparameters, data version, feature set version, and results. The PM reviews the dashboard at the weekly review and confirms the project is ready to proceed to Phase 5 evaluation. Key Domain 4 lesson. Baseline first. Every experiment compared to baseline. Time-based split enforced. Overfitting detected and corrected in Phase 4, not Phase 5. A university building a conversational AI chatbot to answer student questions about academic processes, fees, and schedules. Knowledge base. 200 PDF documents. A labeled test set of 200 question-answer pairs is available for evaluation. Architecture decision. RAG. Retrieval augmented generation. The system retrieves relevant document chunks and passes them to a large language model to generate the answer. The alternative, fine-tuning a custom language model, was rejected due to cost, the need to keep information current, and the risk of hallucination. PM approval required for this architecture decision because it determines the entire infrastructure cost and data security approach. Baseline. A keyword matching FAQ system. Resolution rate, 18%. This sets the bar. Domain 4 for RAG is more complex than for a single model, because multiple components must be tuned. The embedding model that converts text to vectors, the chunk size and overlap used to split documents, the number of document chunks retrieved per query, and the prompt template that instructs the language model. Experiment tracking. Weights and biases is used. Each experiment records embedding model, chunk size, top K value, prompt template version, and retrieval accuracy on the 200-pair test set. After 15 experiments, the fine-tuned embedding model outperforms the base embedding model by 12 percentage points in retrieval accuracy. Top 3 retrieval performs better than TOP1. Chunk size of 512 tokens with 50 token overlap is optimal. Validation result. Resolution rate 73%, exceeding the 70% KPI. Hallucination rate below 5% on the test set. Human evaluation confirms answer quality. PM action. The LLM infrastructure decision. Self-hosted open source model versus commercial API. Required PM approval based on data privacy requirements and monthly cost estimates. This is a Domain 4 decision that is not purely technical. Key Domain 4 lesson. Complex AI architectures require experiment tracking across multiple components, not just one model. PM approval of infrastructure decisions is necessary when they have significant cost and security implications. Each AI pattern creates a distinctive Domain 4 landscape. For hyper-personalization, the primary development challenge is handling sparse user-item interaction matrices. Collaborative filtering approaches. Matrix factorization, neural collaborative filtering, require careful regularization to avoid overfitting on the majority of users who have few interactions. The evaluation metric is not accuracy, it is ranking quality. NDCG and precision at K are the appropriate validation metrics. For conversational AI, as illustrated in the case study, RAG is the dominant architecture for knowledge-grounded systems. Experiment tracking must cover the full pipeline, not just the generation component. Retrieval accuracy must be evaluated independently of generation quality. Human evaluation is mandatory in Phase 5 for overall response quality. Automated metrics alone are insufficient. For recognition, the primary development activity is convolutional neural network architecture selection and training. Transfer learning from pre-trained models, ResNet, EfficientNet, Vision Transformer, is standard. Data augmentation must be integrated into the training pipeline. The baseline should be the simplest classification model that uses handcrafted features. For anomaly detection, the experiment loop must include threshold optimization. Training accuracy at the default threshold of 0.5 is meaningless for anomaly detection. The PM must ensure the team presents precision recall curves and explicitly discusses the business cost implications of different threshold choices. For predictive analytics, time-based splitting is mandatory, not optional. Feature engineering is often more valuable than algorithm selection. An XGBoost model with strong domain-engineered features will almost always outperform an untuned neural network on tabular time series data. For goal-driven and autonomous systems, the training environment is a simulation. Domain 4 must evaluate simulation fidelity before production deployment. A model that performs well in simulation but poorly in the real environment is a simulation fidelity failure, not a model failure. Use this checklist at the end of Phase 4 before proceeding to formal Phase 5 evaluation. On algorithm selection, has the algorithm rationale been documented referencing problem type, data characteristics, and Phase 1 non-technical constraints? Has a baseline model been established and recorded? On experiment tracking, is all team using a single shared tracking tool? Does every experiment record objective, algorithm, hyperparameters, data version, code commit, and validation results? Have weekly experiment review meetings been held throughout Phase 4? On model quality, have learning curves been reviewed to detect overfitting or underfitting? Has fairness testing been completed on the validation set by sensitive group? Has explainability been checked with SHAP or LIME where required? Has the team verified that no data leakage exists in the feature set? On compute and engineering, has compute usage been tracked and stayed within budget? Has the model handover format been agreed with the engineering team? Have operational constraints, latency, memory, throughput, been validated against Phase 1 requirements? On model versioning, are the top candidate models saved with full metadata? Can any candidate model be reproduced from the tracking record? On readiness for Phase 5, does at least one candidate model achieve the technical KPIs on the validation set? Has the team confirmed no data leakage, no unreported fairness issues, and full experiment documentation? Are all stakeholders updated on Phase 4 results? The test set has not been used. Confirm this before proceeding. The test set is sealed until the formal Phase 5 evaluation. Using it in Phase 4 invalidates the evaluation entirely. Let us close.
That is Domain 4. Manage AI model development and evaluation. Quick recap. 16% of the exam. Leads Phase 4. Supports Phase 5. Reactivates in Phase 6 for retraining. 9 steps. Algorithm selection, baseline, training, tuning, tracking, validation eval, fairness, explainability, versioning. 4 risks. Overfitting. Wrong algorithm, no tracking, data leakage. Tracking is non-negotiable. The baseline is not optional. The test set is sacred. Never touched in Phase 4. Next, Domain 5. 17% of the exam. Please share with a colleague. Subscribe. Leave a comment. This is Peter Pham. See you in the next lesson.